Merci Emmanuel de l'invitation. J'avais dit que je ferais le séminaire en anglais, donc je vais le faire en anglais, mais après, enfin, si vous avez des questions, on peut basculer en français. Il n'y a pas de souci. So thank you first, thank you very much for inviting me to give this presentation this morning. So I'm Benjamin Vial. So I did my PhD back in the days in Institute Fresnel, and then I moved to the UK in London. So now I'm still in Imperial College London, but I'm detached to France, to Marseille, in Institute Fresnel. And I'm going to talk about some open source software that I've developed in the last, let's say, 5 years. That I'm going to use to do optimization of photonic devices. And one of the key aspects of this software and various numerical methods is that they are auto-differentiable. So we're going to see what all of that means. And I'm going to, first of all, to introduce you some aspects of optimization, and in particular, topology optimization. Sorry. So topology optimization can be seen as a mathematical procedure to sort of optimize, distribute a material in a given design region for a given set of sources, boundary conditions, in order to be able to maximize the constraints, to maximize, sorry, a given objective function for a given performance of a system. So it's an engineering approach, but underneath that, there are some mathematical tools I'm going to introduce you. Sorry. So yeah, here you've got the sort of like basic tutorial, the Hello World program of topology optimization. So that's in mechanics. So you've got a cantilever beam that's fixed on the right-hand side over here, and you apply a force vertically over here, and you want to maximize the rigidity of the system, to distribute some material in order to maximize the stiffness of the system, or minimize its compliance for a given volume fraction of material that you will distribute in this system. So topology optimization, yes, it has been applied essentially in mechanics, and then as well in structural engineering. Generally speaking, here you have a convention center Qatar, where you find this pillar that maximize rigidity to hold this roof, and that's been designed by topology optimization. So it's used in mechanics, in architecture, in aeronautics, for example. There's this nice paper about a very large-scale design of an airplane wing to maximize its rigidity, but also make it as light as possible. And what interests us today is going to be more about photonics and nanophotonics. So in the last, let's say, 15 or 20 years, there's been a big research effort towards using topology optimization in photonics for various applications. Let's say here you've got, for example, the design of photonic crystals with maximum band gap, the design of multiplexers, of, for example, multiplexers over here, or Z bands in photonic crystal waveguides, and so on and so forth. And so in order to be able to do topology optimization, there are a few recipes that I'm going to tell you about now. So first of all, you define a density function. We call it P. It's something that's continuous in between 0 and 1. So it's to distribute essentially two materials. 0 is going to be material 1, or more often is void or air, let's say, and 1 will be your solid material. You can generalize that to distribute more material, but let's stick with this two material approach. You want to distribute that in some domain of your simulation. So it can be the whole domain or a subset of the domain. And then you want to avoid really, really small features that are not fabricable in practice. Um, so you do some filtering of this density. Here you see an animation that you have a very small random distribution of material, and you apply some sort of filtering in order to be able to have larger filters that have a minimum scale. So it can be done in two ways. Essentially, you convolute your unfiltered density function with a Gaussian function. It's just a convolution, or equivalently, you can solve a partial differential equation that will give you this filtered density. So you can choose it to be isotropic, or for example, here I chose an anisotropic filtering process. Next thing you want to do is to be able to remove the intermediate density values that are unphysical. So you do some projection. So you use this sort of function. It's an example of function. And you increase here this beta parameter in order to have a more and more, let's say, a black and white design um, design density function. And you can generalize this. As I said, you can add more and more levels to distribute more than two materials in your domain. And the final thing is, in our case, we're going to want to interpolate the material permittivity. So you interpolate the permittivity between maximum and minimum value. Here is your filtered and projected density, p hat. M is an exponent that you can choose. In our case, everything that I'm going to present is just going to be one. So you've got a linear interpolation, but there are various ways to do that. You can choose m different than one, or you can interpolate the logarithm of the density function. For example, it's often used when you've got a large mismatch, a large contrast in the two material permittivities that you want to use. So equipped with those tools, we are able to do some topology optimization. So I'm going to show you the algorithm. Essentially, it's gradient descent. It's you start from a point here. That's a representation for a two-variable problem. You start with an initial guess, and you want to compute the gradient to follow it and to find a local minimum of your function. So you initialize your density. It can be random, it can be uniform, it can be a previous design that is already known. Then you apply the filtering and projection and interpolation steps that I just presented. So you get the permittivity distribution, and then you solve your Maxwell's equation in our case with your favorite solver. And then you get the electromagnetic field everywhere. And from that, you can evaluate the objective you want to minimize and the constraints associated. So here the key steps that I'm going to develop a bit further next is to do some sensitivity analysis. So how much does your objective function changes when you change your design variable? And then you update the density according to your optimization algorithm. In our case, we use the method of moving asymptotes that is freely implemented in Python with an NLOpt package. And if it has converged, cool, we've got an optimized solution. If not, we are going back to here and we continue the optimization process until we reach convergence on the objective, or until we reach a given number of iterations. In my case, I use 40 iterations. And then this whole loop is started all over again with your optimized solution by increasing the projection factor in order to have a more and more, as I said, binary design. So here's the gist of the topology optimization algorithm. So the next steps here is to compute gradients, as I told you before. So let's assume you've got a solution vector U. In our case, it's going to be let's say, the electric field that depends on a vector of parameters P of size M. and that is given implicitly through this operator F that you can think of Maxwell's equation in photonics. So you've got this implicit relation here, and we've got now G a functional of interest of dimension n. So very often in optimization, we've got a scalar objective function, or maybe the dimension of the objective function is small compared to the number of variables. So G is a functional that you want to minimize or maximize. One thing you can do to approximate the gradient of G with respect to the design variable Pi is to do finite differences. But it's got two main drawbacks. It's numerically can be inaccurate because you need to choose an arbitrary perturbation step H over here. And it's expensive for large number of inputs and or outputs. So another way of obtaining the derivatives is to solve the tangent linear equation. So explicitly you differentiate your objective function and you obtain this tangent equation. But the issue here is that it's very inefficient because you have to solve that for every parameter P of your design variable. So remember, for us, it's going to be very large with compared to the size of our objective function, which is usually a scalar. So what we do instead is to derive the adjoint equation. So assuming this linear system invertible, we can rewrite the du over dp as this, and you substitute that back into equation 2. You obtain this equation. And the key idea is to name this one bit of the equation as lambda. So this last bit, sorry, as lambda that we call the adjoint variable. And you can see here, now it's a solution with one single extra linear solve, you are able to have the gradients for all your design variable, which is very powerful. So this is what is used is in general in topology optimization. So now you can do that by hand as I presented just before, or you can use what is called automatic differentiation, which can be seen as a general way of taking a program computing a value. In our case, it's going to be our objective function, and automatically design a procedure to be able to find the derivative with respect to the inputs. So there's a whole lot of literature about that. I'm not very much of an expert in that. I'm mainly using libraries that do that automatically for you. But they are, so this is not finite differences or symbolic differentiation. It's really an algorithmic procedure. So you essentially decompose your code in some basic building blocks, interesting function, and then you differentiate effectively symbolically each of the building blocks, each of the operations that you process your data with. And then you multiply everything together according to the chain rule of differentiation. Essentially, it's applying the chain rule, but in an automatic way. And there are, to automatize this, there are a few strategies. So transforming the source code or overloading, sorry, the operators that you use. And this is fairly much related with what is called in machine learning forward propagation or backward propagation. And this is why with the advent of this of machine learning tools, you've got more and more libraries that do that automatically for you. In our case, because we are going to have a much larger number of inputs than outputs, we are going to use the reverse mode of differentiation. So equipped with all of these tools, I've developed over the years some numerical codes that I'm now going to go a bit, to present to you a bit deeper. First of all, it's a finite element code. So it's been implemented with open source library for Python. in my code that is called gypsies. So the geometry and mesh generation is done through Gmesh, which is probably the most popular mesh generator that is developed by Christophe Gezen. The finite element library is another popular library that is called Phoenix. And in our case, we use the second order Lagrange basis functions for the elements. And the gradient calculation that are done automatically is done through Dolphin adjoint, which is an extension to Phoenix to be able to derive automatically the adjoint equation that I talked about just before. So it's got a nice, if it shows, sorry. Yeah, so this is the website of the code, so you can have a look around. You can have some documentation and browse the examples from the code. It shows, yeah, you've got various examples. For example, you can do dielectric gratings, perfectly conducting gratings. So periodic problems in 2D and 3D. Some homogenization procedure if you want to calculate effective indices, model analysis and computation of quasi-normal modes for periodic and non-periodic problem, scattering, and there are various calculation of local density of states, all sort of with user-friendly interfaces to be able to define all of this. And you've got as well so if you click on the various examples, you can have the definition of the permittivities. You can have how you build the geometry using Gmesh, and it's going to solve here. You've got a field map, for example, in this case of a core shell nanorod grating. You can download here the Python scripts and the JPython notebook if you want, and you can also run it online if you click over here. So that's the presentation of the package. So let me go back to the presentation and show you an application of what I've done using this package. For example, we wanted to be able to have a lens that focus energy at two different locations depending on the excitation frequency. This is going to be the objective we want to maximize. So the norm of the electric field at two different frequencies and two different locations. Here you can see the optimization history, and you can see the objective is increasing more and more as you move along the iteration number. Here you can see the distribution of the permittivity. So this was two different dielectrics that were distributed in this square region. And you can see here it goes from a continuous distribution of a material to a black and white a binary distribution. So this has been 3D printed. So actually, there are two dielectrics, but they're the same color, so you can't really see. And those were the simulations for so the results of optimization. So you've got a point source somewhere here coming impinging on your structure from the left-hand side. And at 9 gigahertz, so it's in microwaves, you want to focus energy at the top of the lens and at 10 gigahertz at the bottom of the lens. And those are the measurements that were performed in an apparatus that allowed us to measure the near field in a waveguide. And you can see the results are pretty much aligned with the simulation. So you've got focusing at the top of the lens for 9 gigahertz and at the bottom for 10 gigahertz. That was one of the thing that we can do with this code. And another application was to design superscatterers. So maximizing, essentially, the objective function is maximizing the scattering cross-section for for a given frequency. So here you can see the a little animation that tells you. So those were performed for the two different polarization case in 2D independently, and you can see the movie of the optimization process. So those are the results. So it's been optimized for a wavelength of 600 nanometers. So you can see the scattering cross-section is resonant at this wavelength. And this is also seen in this radiation diagram. So you've got a very strong forward scattering. There's a plane wave coming from the left-hand side over here. Strong forward scattering for TE and TM polarization. And this is also seen by the field maps over here. And then we did with our code as well a quasi-normal mode expansion. So the quasi-normal modes are modes of open systems. And we computed the modes of the optimized structures. So those were I didn't say it, but this is silicon and silica distributed in this region. We did a modal analysis, found a couple of modes, 4 modes that are relevant for describing what is happening. And in the literature, it was said that this strong forward scattering was due to the simultaneous excitation of eigenmodes. So we are able to calculate how much the modes couple to the incident field. And you can see in the T case, there's one mode that is very much excited with other excitation from the other modes. But for the TM polarization case, you've got modes from one side and the other of the design wavelengths, 600 nanometers, that were excited more or less with the same magnitude. So we were able to tell which resonances are being excited by an incident plane wave. The next thing I wanted to talk about is the second piece of code that I've developed. So it's a Fourier modal method. So it's also known as a rigorous couple wave analysis. So it's well suited for a specific type of a periodic structure that are made up of a stacked structured layers. So you can have an alternate different so this is periodic in the X and Y direction over here, different structured layer, and you can have as well in between homogeneous layers. The key idea is to expand the EM field in each layer into eigenmodes on a Fourier basis in the plane of periodicity. And so this has been implemented in Python again. And so for the core linear operations, so for the core linear algebra and array manipulations, within the code, you can choose with different numerical backends, let's say. So NumPy, which is the de facto library for linear algebra and array manipulations in Python, SciPy, which has more algorithm than NumPy, in particular for more particular case, let's say Hermitian eigenproblems or generalized eigenproblems. So those are the two de facto libraries in Python to do scientific computing, let's say. And then Autograd is an extension of NumPy that adds to most of the functions of NumPy automatic differentiation. So you can, if you want to use the automatic differentiation tools, you can switch to this backend. Then there's another backend, which is PyTorch, which is mostly developed for machine learning purposes, but that has got as well automatic differentiation and also GPU acceleration. And another backend is the JAX, which is again another library that has got automatic differentiation, also less developed than PyTorch, and also GPU acceleration. So again, it's got a nice little website. You can go and browse the different examples. For example, here there's should be some of them about convergence of the Fourier model method with a number of harmonics and comparison with the literature. There are some benchmarks to see what the different backends are doing. And there are some tutorials as well on how to define geometries and how to compute gradients um, for, um, for the simulations. So as one of the applications that I've done with this code is to design a meta surface. So we wanted to maximize, for both polarization, maximize the transmission coefficient in one given diffraction order, namely the +1,0 diffraction transmitted order for both polarization at the same time. So it's here you've got the animation of the optimization history and the density function. So 0 is air and 1 is silicon. So we started with an initial design of somehow a pillar, let's say. And here in that case, the unit cell is rectangular. So you can see we've got at the end of the day, when you maximize both values at the same time, you've got more than 90% for T polarization and 85% in transmission for the TM polarization case. And here are the spectra of the optimized structure. So you can see for TM polarization, there's clearly a resonance at the design frequency over here that is clearly mediated by this central nanostructure over here, as you can see on the field maps. And for the T polarization case, you've got a broader response that is mostly mediated by those side nanostructures over here. And this is a 3D rendering of what it could see if someone wanted to fabricate that one day. The last piece of code I wanted to tell you about is a plane wave expansion method. So this is to compute band diagrams for photonic crystals. So this is just in 2D at the moment, but it's generalizable in 3D. Shall do that when I have time someday. So you've got possibly Z anisotropic, so anisotropic in the plane of in the plane in the 2D plane that you consider materials for both permittivity and permeability. Excuse me. That are non-dispersive, that is to say, you stick with the linear eigenproblem. In that case, the polarization decouple, and you can expand the components by applying Bloch theorem, and you end up with this generalized eigenvalue problem. We've got two different expressions for T or TM polarization. And one bit that has been that I've added to the code is a reduced block mode expansion. So you only, instead of solving the equation on the whole of the Brillouin zone, you can solve this equation at symmetry points of the first Brillouin zone and then use those eigenvectors as a basis. And so you have a much smaller eigensystem to solve. And since you are mostly interested in the lowest bands of your band diagram, this saves you a lot of computational resources. So again, it's got some package. So you've got the documentation with the different sides. I cannot read that. Anyways, so you can see different. There are different examples. So can't reach that. I don't know why. Um, Anyways, yeah, I've got various examples. So one thing I was telling you about is the reduced block mode expansion. So you've got the comparisons between the two methods. So this is the full band diagram computation, and in dash line you've got the reduced block mode expansion. You've got a very nice agreement between those two, and a very nice speed up um, between those two as well. And one thing I did very recently is to be able to compute topological invariants in those photonic crystal and those photonic crystals. So in that case, we've got a medium with anisotropic permeability. So when you apply a magnetic field, it becomes anisotropic. So without a magnetic field, you don't have any band gap between the second and third band. And when you apply a magnetic field, you open a band gap. And you can calculate what is called the topological features, so the Berry curvature, and then integrating that in the first reduced Brillouin zone, you can compute the Chen number. So this is for the first band. The Chen number is 0. This is, yeah, so numerically this is 0. The second band is non-trivial, so you've got a -1 Chen number, and the third band is non-trivial as well, with a Chen number of 2. Let's go back to optimization of photonic crystals. One of the things I've done is to try and design the unit cell in order to maximize the band gap between two bands. So we are anti-polarization. We want to distribute those two materials, and we enforce the symmetry. We enforce C4 symmetry on the unit cell. And we wanted to maximize the band gap between the band number 5 and band number 6. Sorry. So I replace the movie here. And this is done very easily with all the auto differentiation tools that I've presented before. And the finite distribution is in agreement with some very simple geometrical rules that are given in this paper. It's essentially the walls for T polarization of an optimal centroidal Voronoi tessellation with n is equal to 5, because we are in between the 5th and the 6th band. So that was one thing that we've done with this code. And the other thing was to do some dispersion engineering. So let's say we want to have this target dispersion curve in dashed gray lines over here for a given band. So we want to minimize this functional over here. We don't very much care about where this is about let's say the average value. We just care about the variation of the dispersion. And you end up with this topology inside the unit cell. Here we enforced symmetry along this axis over here. And at the end of the day, you've got a nice dispersion engineered photonic crystal. So to summarize, it's all well, I've been doing this open source software as a collection of some codes that I had. You can see the downloads over time over here. So it's got it started really as I was bored during COVID, so I was like, I'm going to gather all my codes and try to learn how to distribute all of that and package all of that nicely, so people can possibly use that. So the advantage, yeah, well, that's low cost, since it's open and free. It's portable, so it's customizable, and you can inspect the source code, do whatever you want with it, depending on the license, and also vendor independence. I chose as it is a widely package manager to easily install everything, and it also fits in the larger picture of the a very vast and rich scientific Python ecosystem. Hopefully, it's going to enable reproducible and collaborative research, and most importantly, I thought auto differentiation tools. Now there are a lot of libraries, as I told you, that have exploded with the advent of machine learning, but we can use them to do photonics and optimization in order to explore cool designs and materials, meta materials, or meta surfaces with improved performances. So if you want to get the code, it's developed on GitLab. So everything is tested normally when you push to the repository. So it's called continuous integration. And also it builds all the website and the documentation automatically. So just go if you want to try it, install it, fork it, run it online, report bugs. I'll be more than happy to collaborate on that. So it's for Gypsys and Nanos, it's installable with pip and Conda, which is another package manager. And for Protis, for the plane wave expansion method, it's installable by pip. Here is a freeware list that I found on GitHub. So it's at this repository. So there are like there is a collection of open source tools for photonics. So it's sort of sorted with what the tools do. So visualization, simulation, layout, building. And for what mostly interests me, it's mostly the simulation codes. It's sorted with different numerical methods. So it's a very interesting tool. And if you've got your own open source software, you can go there, open a pull request, and add it to the list so people can find it. And with all of that, I thank you very much for your attention. I'll be very happy to answer your questions.